So hello everyone, this is lecture 8 for the electricity and magnetism. In the last lecture we were discussing about the properties of the conductor. So let's see some examples. So we have thick conducting cell. This is thick conducting cell means you have some cavity here and this is dielectric sphere, something like that. And it is a cell because we have a hollow space here. Now electric field inside this surface will be 0 because this is conductor, and this radius is A and this radius is B. So we have some cases based on this. So first Q charge is given to the shell, means Q charge is applied here on this. Now see, this is conductor, then this Q charge will go to the surface, and surface means on this surface. So the net charge will be plus Q over the surface, and the charge density, if you see at this A surface, will be 0 because complete charge will go to the surface. That's the property of the conductor. And sigma v will be Q by 4 pi b square. So see, this charge can't go here, otherwise there will be net electric field here. That's why this any charge given to this cell will go to the surface of this outer surface. Okay. Now minus Q charge is at the center. So now minus Q charge is here. So the plus Q charge will develop here. So that inside the total electric field inside here will be 0. That's why plus Q is here, then minus Q will develop here. And plus Q will be at the outer surface. So density at sigma A will be plus Q divided by 4 pi A square, because minus Q is at, so plus Q will be here and minus Q will be here. So minus Q by 4 pi B square at the B. So it was plus Q, then minus Q will be here and plus Q here. So that's how it works. Now third is minus Q at the center and plus Q to the cell. So minus Q at the center and plus Q to the cell we have applied. So minus Q at the center means plus Q will develop here and minus Q will be here. So minus Q here and plus Q is already here. So this will give you 0 at B, and A at, it will be plus Q inside. So total field means charge density will be Q by 4 pi epsilon A square at the A surface. And minus Q here, plus Q here, and then again minus Q here, and plus Q is already there. That's why sigma V is 0. Now fourth is minus Q at the center and plus Q to, plus 2Q to the cell. So again minus Q here, plus Q here, then minus Q here, and 2Q applied. So 2Q minus Q will give you Q. So Q and Q, the total charge density will remain same at A and B. It will be Q by 4 pi AX square, Q by 4 pi naught B square. So these are the different conditions you must know. That's how the conductor works with the charges. So let's see some examples based on them. A metal sphere of radius r carrying charge q is surrounded by a thick concentric metal cell. So metal sphere, and it is carrying charge and it is surrounded by a thick concentric metal cell. Inner radius is a, outer radius b. The cell carries no net charge. Find sigma at r, a and b. Find potential at center. If outer surface is touched to the ground, find the sigma and potential at the origin or the center. So it's just a similar case, means now we have a conducting sphere inside this cavity, and then we are working on this, means the conductor is here and having the plus Q charge. So we have this thing, and this is your cell. So this distance is A, this distance is B, and this is R. This is the conducting sphere, this is conducting cell, and plus Q charge is already on it. So what will be the density? This plus Q here, then on the A surface it will be minus Q, and here it will be plus Q. Sigma r will be this, sigma A is minus and sigma B is again plus. So that is the first part. Now we need to find the potential at the origin. So for that we need to take the infinity to this point. The total formula is infinity to 0, limit E dot dl. Now electric field will change from this at this area, in this region, in this region, in this region, and in this region. So for this region electric field will be 0. Inside this conducting sphere electric field will be 0. So if we consider E1 here, E2 here, E3 here, E4 here, so E1 will be 0 and E3 will be 0, and E2 will be plus Q charge here, so it will be Q by 4 pi naught R square, and E4 will be, this is plus Q, then minus Q and plus Q, so here it will be plus Q over 4 pi naught R square. So we have different electric field for the different ranges, so we'll just separate this limit. So minus infinity to B, then B to A, then A to R, and R to 0. So this E3 and E1 is 0, so E3 E1 is 0. We will need to only solve these two terms, put the value of electric field, and just integrate. It will give us this. So V at the origin will be Q by 4 pi naught 1 upon B plus 1 upon R minus 1 upon A. Now the third part is, if the outer surface touches to the ground, now we have connected this to the ground. Means that net charge on the outer surface will be 0, means E4 will also become 0. Others will remain same. E1 will be 0, E3 will be 0, and E4 will be 0. So we have only E2, and E2 ranges a to r. So we just need to solve this a2 dot dl, and we already know e2, so this will give us the potential at the origin. This will be your answer. And now the densities will change, means only b will become 0. At r it will be remain same, q by 4 pi r square, and a it is minus q by 4 pi a square. So it is the same thing. Let's consider next case. Two spherical cavities of radius a and b are formed in the interior of a conducting sphere of radius r. At center of each cavity, charges q and qb is placed respectively in cavity a and b. So we have cavity a and b. Inside these cavities, you have placed charge qa and qb, and this is a conducting sphere. Okay, and this radius is r. This is a sphere. So what we need to do is find sigma a, sigma b, sigma r. So we need to find the density at this surface, and this surface. So see, qa is here, so minus qa will be developed here, and qb is here, so minus qb will develop here, and minus qb will give plus qb outside, and minus qa will give plus qa outside. So outside total charge will be qa plus qb. So sigma r will be qa plus qb divided by 4 pi r square. Now here charge is minus qa, so it will give us minus q by 4 pi square, and here charge is minus qb, it will give us this. So this will be your densities. Now find field outside the conductor. So we need to find the outside. So total charge is this. So qa plus qb. So outside electric field will be qa plus qb divided by 4 pi epsilon r square r cap. Now C part is find field within each cavity. So inside its cavity, total charge is qa. So it will be qa divided by 4 pi epsilon and the distance. So r less than a. This will be your electric field inside the a cavity. Inside b cavity, it will be this. Now D part is what is the force between q and qb. So there is no penetration of electric field inside this conductor. Electric field can't penetrate. That's why this cavity or the charge won't affect anything to this. So there will be no force between them, that is 0. So this D part is 0. Now E is, if a third charge QC is placed near the conductor, which of the above answers will change? If you place some QC charge here, then which of the answers will change? See, this charge can't penetrate this, so inside nothing will change. But this charge will change the charge distribution over the surface. It will just unsymmetrically, then charge will distribute, minus will came here, plus will came here. Net charge will unsymmetrically distributed over it. So only the sigma r charge density over the surface will change, and the field outside conductor will change at different point because of the unsymmetrical charge distribution. So only these two things will change. There is the sigma r and the b part outside the conductor. So I hope it is clear to you now all the properties of the conductor. Let's discuss now the electric dipoles. So what is a dipole? It is a two charge with the same magnitude and the opposite, means plus and minus q. So these are making the dipoles. So we have small dipoles. Let's discuss. If these are plus q and minus q charge and distance between them is d, and we need to find the potential at some point p, which is a distance r. Now this r is very large, means very large as compared to this d. Then we'll call this dipole as a small dipole, and it is written as p, and p is equal to qd, means charge and multiplied distance between them. This is called the dipole moment. Now you can assume this like you have an atom. This is uniformly distributed charge. Now if you applied some electric field from this side, so minus charge will came this side and plus will charge this side. So this will shift like this. So you will develop a dipole. And dipole direction is minus q to plus q. So it is in the same direction as E. So this is called the means polarizability, we call this, and P can be defined as alpha E, where alpha is the atomic polarizability. This is dipole moment in electric field. So that's how we define the small dipole. Now we need to find the potential at this p point due to this dipole. So the formula simply, due to this and due to this, sum of these two potentials, it will be q by 4 pi epsilon naught, and this r plus, and q minus q by 4 pi epsilon naught r minus. So this will be your formula. Now we need to find this value 1 upon r plus and r minus. So let's find it in the polar coordinates because we have theta and the r. So let's do that. Now if we make this complete right triangle, then this distance will be r sine theta, and this will be r cos theta. So we can just write this r plus s equal to r cos theta, this minus d by 2 whole square plus r sine theta square will give you r plus. So r plus square equal to r cos theta minus d by 2 square. Using the Pythagoras theorem, just this distance plus this distance square will give you r plus. So this distance is nothing but r cos theta minus d by 2. So this will be your thing. Now just to open it, you will get this thing. Now this r cos square theta and the r square sin square theta will give you r square, d square of 4 minus rd cos theta. Now see, take the r square common, this will give you this thing. Now this d is very small as compared to r, and this term will be very small, so we'll neglect this. So we'll get r square 1 minus d by r cos theta only. And now take the square root of this. It will give you, and square root and the inverse, it will give you, means reciprocal, it will give you 1 upon r, 1 minus d by r cos theta minus 1 upon 2. Now using the binomial expression, you will get 1 plus d by 2r cos theta here. And same you can apply for the 1 upon r minus, it will give you 1 upon r 1 minus d by 2r cos theta. Now you just substitute here, take q outside, 1 upon r minus 1 upon r minus 1 upon r, this will give you d by r square cos theta. Substitute at the upper, you will get the potential, that will be Vr theta equal to q by 4 pi epsilon naught d by r square cos theta. So this is the potential in the polar coordinates. And Vr theta, we also can write qd is equal to p, that is dipole moment. So we can write p cos theta divided by 4 pi epsilon naught r square. Now see that this dipole is moment direction is z cap, because minus q here and q here, so minus q to q will give you direction, so it is in the z cap. And this is r in the r cap directions. P dot r cap we can write p as p z cap. Z cap dot r cap will give you cos theta, because the z cap r cap will give you cos theta. So this p cos theta can be written as p dot r. So we can write this complete form in this way also, p dot r 4 pi epsilon naught r square. So that's why we absorb this theta, and this is also called the coordinate free form. So that's all for today. In the next lecture we'll discuss more. So we'll see you in the next lecture.